In exercise 8c, we look at how a binomial distribution can be approximated by using normal distributions, provided that the sample size is large. Not only will this allow us to calculate probabilities, but also enables us to apply the theory of normal distributions to binomial distributions. Now remember that a normal distribution, our random variable x, we have this expression to represent the normal distribution. We have the mean and the square of the deviation. For a binomial, our random variable x, we would write bin for binomial, and then we have the sample size and then the probability of success. Now, investigation 3 in your textbook will look at the shape of binomial distributions, and we look at what happens as n gets larger. Here we've got from 20 up to 50, and when the probability changes from 0.1 up to 0.9. There is a simulation which will be attached to the weekly notes, which I'll run through. This is what the textbook software looks like. So at the moment we've got n is equal to 50, and we've got chance of success is 0.6. Now if you hit the next button here, it'll then work out the mean. Once again, n times by p, so 50 times by 0.6 will give us 30, and the deviation is the square root of n times p times q, and that's been worked out for us here. Alright, so there's our np, there's our n times by q value there. Right, now if we were to change the sample size, so let's make that down to 20. Right, and our probability, we'll make that 0.1. Right, it calculates the mean for us here and the deviation, and we can see the curve is slightly positively skewed, not a normal curve. So now change to p to 0.3, and we can see the skewness is gone and it looks more symmetrical. P 0.5 is even more symmetrical. Up to 0.9 for P, we can see now it looks to be negatively skewed. Alright, let's see what happens when we change the sample size here. Make it up to 50, and let's bring the probability back to 0.1. Alright, so we can see it's not as much skewed as the value was when P was 0.1 and M was equal to 20, but it is still not quite symmetrical. Let's bring up the probability to 0.3. We have a much more symmetric shape. Let's go up to 0.9, once again a little bit skewed. Now I've changed n to 70, probability is 0.1, once again not quite symmetric, but not too far off. If we'd increase our value of p, 0.3, symmetrical there, 0.5, still symmetrical, we'll go to 7, and we'll go to 9, a little bit asymmetrical, but not too bad. Alright, finally we'll go to n equals 100. Oh, that's not too bad in terms of symmetry. Let's reduce our probability down to 0.7, 0.5, 0.3, 0.1. Now, don't forget you could draw similar type graphs using the graphics calculator. We can graph the spike graph if we know the value of n and the value of p, and that was done last exercise. Alright, so from the investigation, in summary, what we find is that when np and n times q are both bigger than 10, then the graphs become more symmetric. And in general, as the value of n increases, then the binomial distribution more closely resembles a normal distribution. symmetric curve. So summarising, if we have a binomial distribution with n the sample size, p the probability of success, then we know that we can work out the mean and deviation using this. And we know now that the distribution itself is approximately normal, bell-shaped curve. The larger the value of n, the better the approximation to a symmetrical curve. And our rule of thumb is that both np and nq, or n1 take p, are both bigger than or equal to 10. Now, in the example, fair coin tossed 1,000,000 times, so obviously n is large, and x is the number of heads which can result, and so we have a binomial, so it's either heads or not heads, and m is 1,000,000, the chance of having heads is 0.5. Alright, checking that np and nq are both greater than 10, so n times by p is going to equal 1,000,000 times by a half, that's going to be 500,000, which is obviously bigger than 10. Alright, and n times by 1 take p, so the same as n times by q, which should in fact be the same calculation. It'll be 1,000,000 times by a half. So, in each case we have a value greater than 10. Part B, working out the mean. So the mean is equal to n times by p, which we know is 500,000. And the deviation, our formula was n, p, and then 1 take p, or q, and the square root thereof. So np is equal to 500,000, and we times that by 1/2, and take the square root of that, which gives us an answer of 500. Now to do part C, working out the probability that exactly 500,000 heads result, we can now use a normal approximation because we satisfied these constraints here. So if we use the calculator, we go to stats mode, and you choose distribution. Now rather than choosing a binomial distribution, we can choose a normal distribution, and you're working out the probability at one instance, not a cumulative calculation, so NPD, and enter the values. We have the deviation and the mean worked out. We want our situation and execute on that, and we end up with an answer of 0.00007978. Now part D, we want to work out probability between these two values, and it is inclusive. So once again, we can use a normal approximation rather than a binomial. So distribution and then normal distribution. Here's an NCD. So we are between 499,800 and 500,200, and our deviation and mean do not change, and we end up with a probability of 0.3108. And that should be enough to get you started on exercise 8C.